When a megawatt-scale industrial pump grinds to a halt under extreme thermal stress, the resulting momentum can jeopardize an entire data center. In a Tier 4 facility, preventing that failure from cascading is not left to chance. System readiness is a highly controlled, engineered condition. To maintain that condition, operators follow an absolute rule. No intervention occurs without explicit authority, mathematically proven capacity, and time-aligned digital evidence. This diagram maps the physical inventory of the thermal service path. Heat moves from the IT load demand through liquid-to-air terminal units like computer room air handlers and into the primary and secondary hydronic distribution loops. From those loops, the heat transfers to the rejection plant at the outer edges of the system, utilizing air or water-cooled chillers, and eventually expelling into the atmosphere through open or closed-circuit cooling towers. Managing this thermal path requires defining strict interface ownership at every physical boundary. This flowchart tracks the system from IT demand on the left to heat rejection on the right. At every handoff point, capacity must be declared and acceptance confirmed. Below the main path are the shared dependencies that support these components. Standby power generators, control networks, and makeup water systems are single points of vulnerability that interact with the entire cooling chain. The physical plant is governed entirely by the controlled document hierarchy. This pyramid dictates exactly what operational conditions are allowed, starting from the foundational design basis at the top. The middle tier defines the daily execution documents. Operators use standard operating procedures for normal, repeatable tasks, methods of procedure for planned work, emergency operating procedures for abnormal events, and equipment maintenance plans for recurring physical upkeep. This operations governance matrix outlines exactly who holds authority over these procedures. While facility operations own the 24/7 monitoring, the data center manager holds ultimate accountability for risk and budget decisions. During an emergency, the dynamic shifts. The operator leads the immediate response to stabilize the plant. However, they can only authorize a return to normal service after an independent review of time-aligned digital evidence proves the system is safe. Physical infrastructure relies entirely on this rigid, hierarchical documentation structure. Without it, human interaction with high-voltage, high-pressure machines introduces unacceptable risk to the IT load. This operations scorecard dashboard illustrates a key distinction. Component uptime does not equal system service impact. A chiller can have a high mean time between failures, but if its downtime aligns with a peak load event, the service is compromised. Notice the warning banner at the bottom. Relying on blended KPIs can mask overdue work on specific, highly critical assets. Gaps in protective equipment must be tracked individually to maintain true redundancy. The highest risk of failure occurs during human shift transitions. To eliminate tracking errors, incoming and outgoing teams execute a mandatory 30-minute synchronized handover, logging active alarms, bypass states, and ongoing maintenance. Beyond digital monitoring, frontline defense relies on sensory patrols. Operators use sight, sound, smell, and touch to detect weak physical signals, like the scent of burning insulation or an irregular pump vibration, long before automated alarms trigger an escalation. Early detection through direct human vigilance, combined with strict handover protocols, forms the first line of defense against compounding mechanical failures. This circular diagram illustrates the readiness engine. Readiness is not a static achievement. It is a continuous, controlled operating cycle moving through phases of governing documentation, isolation of assets, rigorous testing under load, and continuous learning. This thermometer gauge defines the operating envelope. An envelope is a combination of allowable ranges, duration limits, alarm boundaries, and specific recovery actions across normal, maintenance, and failure states. Having physical assets installed does not guarantee system maintainability. Before taking any equipment offline, operators must mathematically prove the residual capacity margin. The calculation in the math pipeline box proves this point. You take the total installed duty, subtract the isolated asset, and subtract the live load forecast. Here, that leaves a razor-thin residual margin of exactly 0.15 megawatts. If the next credible failure drops capacity further, it creates a 1.2 megawatt deficit. Mitigations and strict IT load ceilings must be established before maintenance work begins. To enforce these limits, facilities use a maintenance release gate. No physical work starts until 4 independent operational conditions are simultaneously verified and satisfied. The live load capacity must be proven below available duty. Isolation requires identifying the smallest safe segment with 0 stored energy. Independence ensures alternate control paths are entirely outside the failure domain. Finally, human factors activate a 2-person interlock with clear stop work authority. Stripping away mechanical redundancy to perform maintenance introduces immediate vulnerability. Protecting the live IT load requires deterministic, unyielding physical and procedural gates. Once approved, work follows this 9-step maintenance execution sequence. Yellow lock icons denote rigid hold points, where operators must stop and verify safe capacity and isolation before proceeding. Hold point 2 demands hardwired physical energy isolation. This requires the application of OSHA standard multi-padlock lockout-tagout hasps, securing the plant state and protecting the technicians downstream. This comparison matrix outlines 3 approaches to maintenance. While scheduled interval work handles predictable wear, condition-based maintenance is crucial because it triggers interventions based on measurable degradation, allowing operators to act before a failure occurs. This deep dive into chillers and heat rejection shows the specific condition inputs operators track. The charts highlight emerging failure signatures, like spikes in compressor triaxial vibration or subtle downward drifts in evaporator approach temperatures. Isolated maintenance provides a window to hunt for hidden threats across the distribution network. A single failed shared valve can silently bypass coolant and entirely defeat the redundant computer room air handlers and direct-to-chip cooling loops. This funnel diagram illustrates how methods of procedure pass through a risk-based change review board. Every planned action must outline authorization scope, controlled execution steps, and verification methods. Crucially, every procedure establishes a point of no return. If expected plant responses fail at or before this threshold, operators must execute a pre-verified rollback plan to restore the previous safe state. Physical reassembly is only half the job. Before a system can return to automatic control, its signals must pass through the data quality gate to verify range, accuracy, and calibration. The strict rule for acceptance is that the initiating event, the operator's action, the equipment's physical response, and the restored state must all share one time-aligned digital record. Without synchronized, calibrated telemetry proving that the restoration holds under a representative IT load, the maintenance intervention is operationally incomplete. When critical faults bypass predictive maintenance, operators work under a strict 1 to 2 minute containment SLA. The immediate priority is not diagnosing the broken component, it is intercepting the rising thermal load and stabilizing the service. This hexagonal diagram maps the 6-step troubleshooting workflow used to systematically contain and correct a fault without inducing secondary errors. Step 1 dictates starting thermal energy storage or alternate standby paths first. By Step 3, operators must cross-check local physical gauges against the control system to validate sensing and rule out false signals. The center warning box highlights the absolute rule of emergency troubleshooting: troubleshoot from evidence. Never defeat local protective safety logic to force an equipment restart. This matrix dictates exact responses to edge case scenarios. For a sudden chiller trip, operators instantly start alternate paths, validate the hardware safeties, and preserve the digital trip snapshot before touching the physical unit. In the event of a hydronic leak, the protocol is to isolate the smallest possible pipe segment and deploy wet vacs. The overarching diagnostic focus remains strictly on protecting the IT inlet temperature limits above all else. To prevent leaks entirely, operators monitor closed loops for unexplained makeup water increases and carefully track cycles of concentration and blowdown rates in open systems. In an emergency, state is not achieved by rushing. It is achieved through strict adherence to pre-vetted procedures, which prevents the panic-driven manual overrides that frequently cause catastrophic cascading failures. Extreme events demand specialized protocols. A severe refrigerant rupture requires automated mechanical evacuation to comply with EPA Section 608. Following a seismic event, operators must perform mandatory structural audits of pipe headers and spring isolators before restarting any vibrating equipment. This matrix shows that emergency recovery relies heavily on on-site logistics, specifically a strategy called component infant mortality deflection, which mandates local, climate-controlled storage for exact replacement parts. The SLA mandate for items in the critical zone, such as PLC input-output modules and custom sensors, requires that they be hot-swapped from on-site stock within 1 hour to prevent losing control loop visibility. To execute these complex recoveries, new teams follow a strict 90-day competency timeline. As shown in this staircase model, staff transition from learning baselines and freezing as-builts to executing live procedures. To meet the Uptime Institute operational sustainability mandate, this training culminates in quarterly, unannounced stress drills. These blind simulations and safe fault injections test the team's reflex actions directly under pressure. Tier 4 reliability is a deterministic achievement. When a megawatt-scale failure occurs, operators do not miraculously rise to the occasion. They fall to the exact level of their operating evidence, their established methods of procedure, and the rigor of their stress drills.